So welcome to our second lecture, where according to our schedule, the first topic to look into would be the foundation of descriptive analytics, which in a nutshell is one branch of business analytics. It's one of its flavors. That said, I certainly realized that in the last week we were too eager looking into credit scores and what Schufer is doing as an analytics company, and that there was some content which we did not quite look into. You know, foundational content, definitions. So before we will look into descriptive analytics, I copied some of the slides that we left out last week and which I felt actually are important into this slide deck. And this is what we will start with, a brief refresher of what business analytics is about. And then afterwards we dive into descriptive analytics and learn more about one of its main flavors, which is cluster analysis. For the majority of you, I expect that also to be a little refresher. Commonly, that is a topic, cluster analysis, which is covered in undergrad courses. Maybe you even went into my undergrad course where I talk about cluster analysis as well. It's still useful, I'm sure, to, well, remind ourselves what that is and to see where it fits in when talking about business analytics. So without more introduction, let's move ahead. Business analytics revisited, and as always, when you have any questions, issues, please let me know. Now, boring definition time. That's one of the bits I left out last week. Certainly we find textbooks and online resources that provide a crisp, carefully thought through definition of what business analytics might be. I took one from a textbook by Evans. The definition is what I like about this book. It was one of the first books on business analytics, and well, you can read it for yourself. Analytics, or business analytics for that matter, concerns the use of data, IT, statistical analysis, and quantitative methods, difference being question mark, never mind, and mathematical or computer-based models, difference being question mark, never mind, to help managers gain improved insight about their business operations and make better fact-based decisions. I mean, the last bit, I would argue that this is also what we established last week, this notion. Supporting decisions by processing, analyzing data, and equipping business users with the tools they need to process and analyze data, whatever processing means and whatever analysis means. Evans provides us some insight what that could mean, referring to statistical analysis, for example, and we will look at that in more detail very shortly. You also see this nice colorful picture on the right-hand side of the slide, which I identified by using Google image search, business analytics definition. Several colorful pictures pop up, including this one. What I am trying to emphasize here with this graph is that just in case you have taken previous courses on related topics, maybe my undergraduate course on business intelligence systems or similar courses, the definition part, neither the verbal definition nor the visual definition, i.e. the graph, might really surprise you or might not appear as something fundamentally new, and they are not indeed. The picture, for example, refers, in my opinion, to a standardized technology stack. A technology stack that we've been talking about in the scope of business intelligence for decades by now, that includes the gathering and management and integration of data and its examination or analysis using different front-end tools. So it's not really new, or it does not appear as fundamentally new, the whole concept, and certainly it is not. I would recommend you judge it as an evolution of previous concepts that have been around, how IT can support decision making. Something that is much more important to me would be the graph on this slide here, which is the set of what business analytics is all about. And we find 4 flavors: descriptive, diagnostic, predictive, and prescriptive analytics. So consider these the main branches into which business analytics splits up. Even in Evans' original textbook, you find 3 of these: descriptive, predictive, prescriptive. Arguably, these are the main ones. And then if we browse around, looking into other textbooks, looking on the web, we commonly find a 4th branch or flavor. Sometimes it's called diagnostic. This goes back, I believe, to Gartner Research, who coined this 4th branch, diagnostic analytics. In other definitions of forces, you might see visual analytics appearing as 4th branch. So there is some variance. The other 3 are kind of set in stone, and they, refer to different paradigms, how decisions can be supported using IT and computer-based models. Descriptive is on our today's agenda. So in a nutshell, data is all around, omnipresent, typically huge and complicated. Finding ways to describe it in the way that business users can digest is a core goal of descriptive analytics. Predictive, as the name suggests, is all about forecasting the future. And note that there is a crisp difference between describing and summarizing the present and the past, descriptive analytics, and anticipating what is going to happen, predictive analytics. The term prescription then embodies a strong normative element to prescribe an action, to tell somebody what to do. I prescribe you to attend the tutorial. That's a very concrete action, what you should do. So prescriptive analytics goes into the direction of automating decision, which is a very specific form of supporting decision by taking the human decision maker out of the equation. That is a way to support people, of course, and it's fundamentally different from a means of supporting decisions by providing information, aggregating, summarizing, and visualizing complex data. So please note these arrows on the far right-hand side, which are meant to help you understand the core of each of the 4 branches and what it really is about. Gradually moving from a continuum where in one extreme we just provide people information and equip them with tools to pull information they want to see and maybe organize it in a way they want to see it, doing graphs, calculating simple statistics, for example. And on the other extreme, we have maybe artificial intelligence, the robotic system, which handles complex decision settings entirely on its own and maybe only need an element of human supervision to make sure things don't go riot, but other than that, take care of the whole decision setting. These are the 2 extremes that you must take in mind. It's super important. And then each of the 4 branches embodies a set of tools, let's say. We will focus on the predictive part today. We'll briefly sketch the descriptive part. The diagnostic part encompasses, in my opinion, 2 main elements. One element would be to visualize data, to diagnose cause, consequence relationships in a less formal visual way. That's one flavor here. Or the other flavor could be a tool that allows you to play with statistical testing. If you diagnose something that could translate into carrying out hypothesis tests, that is another possible flavor here. We will cover that briefly, but more as part of other chapters. And prescriptive analytics we do not cover in this course, unfortunately, because of the strong normative element, telling people what to do. The traditional academic discipline concerned with the tools that come into play here would be, for example, operational research. So I invite you to attend courses by my colleague Max Klim, for example. Mathematical programs, finding optimal solutions to clear, defined, structured problem formulations. If I know an optimal solution to a problem, what decision do I have to take? The decision is there. I do whatever is optimal, right? So optimization, OR, fits nicely into prescriptive analytics. What econometricians do when they research treatment effects, for example, also fits in here nicely. That is a branch we will briefly cover. And lastly, reinforcement learning is a flavor of machine learning that is unfortunately not part of this course, but is actually the flavor of machine learning which is closest related to what artificial intelligence is all about. So it's very interesting. Stay tuned, attend more courses in these realms, and you learn about reinforcement learning. It's a prescriptive element within business analytics, but not part of this course. Another slide I left out, which is important, would be this one, which I copied from my good friend Bart Barthens and his online learning platform bluecourses.com, where we host a couple of interesting data analytics courses as well. Bear with me for this little advertising break. Check it out. It's a very cool platform. No matter whether you do descriptive or predictive analytics, and to some extent also for the other flavors, diagnostic and prescriptive, or if you use an entirely different term to refer to what you're doing, if you analyze data, if you work with data, and if you try to turn data into insight and eventually decisions, then you will typically find yourself in a multi-step process. And this is a model of this multi-step process and the individual steps it involves. In business analytics, when we look at data processing through the lens of a business organization, through the lens of managers and knowledge workers, the first task really, before we talk about data, IT, stats, or anything the like, is to understand what's our problem. What is the problem and what is our goal? What's the use case we are in? That's the first thing to do and to become clear about. It's especially important in projects where you have different roles, business roles and consultant roles, for example. We, as data scientists, are sometimes too eager and too quickly with drawing upon our expertise of statistics and math and R and Python and all these cool technologies, and believe we can solve all problems there are with these technological power. Often we cannot, and well, in generally understand the problem well, the requirements, the business requirements, the characteristics is really key to having not only a good but even a viable solution. Okay, then once we achieve clarity about the problem, we still want to play with our technologies, and we still want to capitalize on our expertise with processing data. So what data sources do we have access to? Internally in the organization, maybe externally, what data is there? What other data that exists might be relevant? Narrowing down the type of data we will look into, then cleaning it to readying data for subsequent analysis. These are the types of steps we go through. We will then become a bit more technical. Once we have a clean set of data available, we will massage it a little bit in order to help our algorithms performing their job. That's data transformation. And eventually, we come to the stage where we apply some cool algorithm. And although, admittedly, also for this lecture, we will talk a lot about how these algorithms work. And you know, you understanding how they work and you being able to apply them is a key teaching goal for me and my colleagues, of course. Still, always bear in mind this process model. It's just one step. It's by far not the step that consumes the time in real-world projects and is responsible for the costs of analytics projects. The application of the algorithms is really easy in comparison to the other tasks. And it's also the single task in this process where there is the highest potential for automation. Nowadays, companies hunt analytics talents, people who are able to apply these algorithms, know how they work, understand what can be done with that. Nowadays, this is a rare resource, people who are able to do that. And we will make sure you possess this skill, which is currently heavily sought at the job market. But note that there is potential to really commoditize that skill. That's something that can be automated as well. And tools that do that exist already today, maybe in a sort of initial stage, but I would expect these tools to be more advanced, become more and more advanced. The algorithmic part will, in the not too far future, I believe, to be commoditized so that it's really this dual perspective of knowing what the math can do and understanding what businesses need. This is what's gonna, what you need, and once you are there, what you will be able to profit from in many ways. Okay, as far as the data is concerned, let me introduce some terminology. In this course, and many business use cases, we will look into tabular data. Like this one here, this table. We have rows, we have columns. For each of these, the rows and the columns are many terms that exist, all meaning the same thing. The rows of our data table might be called observations, examples, cases, data items, data points, many terms, all meaning the very same thing. I might not be entirely consistent in my slides. Personally, I like the term observation a lot. The data point is something that we observe. It's maybe a customer visiting our online shop, browsing through products. It's something we see in the real world. Unfortunately, observation is also the longest term, so it's not always very handy speaking about doing slides. There is even more diversity when we come to the columns of this table, which statisticians might refer to as variables or covariates. Machine learners tend to call attributes and sometimes features, although feature can mean something slightly different. Predictive is another term that might be used. It is sometimes confusing with so many terms, typically meaning the same thing with maybe subtle differences to understand what it is all about, but this is something we just need to get used to. We can't help these terms exist. It's an interdisciplinary field which we are finding ourselves in. Machine learners, econometricians, statisticians, mathematicians, business analysts, controllers, IT people, they are all joining this game and they come with their terminology. So these are the most common terms, and more importantly, it's the structure. We focus on tabular data, and this is also called structured data because the columns enforce a structure. We have individual items in the cells of that table, and these are to be understood considering the structures that the table enforces. All right, now this is the data we will look at. This is also the data that you work with in the tutorial once we move beyond the introductory part. So to conclude this part, some notes on related terms. One being big data. It's a term that is already past its peak of popularity and maybe inflated expectations, but it is still around. It's maybe a misnomer. A misnomer in that it's too easy to have an intuitive understanding of what big data is about, but intuitively you think about the size, and certainly you note that, oh, right, yeah, sure, there is more data around today than there was around a couple of years ago. And probably you have come across one or two of these statistics that basically show how every day in 1919 more data is generated than all amount of data that ever has been generated since whatever to 1910 or so. These statistics update every time. But obviously we all know there's a lot of data around and even more data being generated. So okay, there is big data, we are in the big data age. But originally this term was coined by a Gartner analyst. And what he really was referring to is a triangle of characteristics. He had 3 V's. Volume, so yes, there is a lot of data around, volume, size, but he also had variety and velocity. Variety meaning that data is not only tabular anymore. So here he was referring to the vast amount of unstructured data, text data that originate, for example, in the scope of social media and Web 2.0. And with velocity, he was referring to the frequency with which data arrives, but also gets outdated. And here the use case would be sensor type of data. We all use sensors every day. Our smartphone is the most popular sensor that exists on the planet today. Maybe it will be replaced by some smart wearable in the future. And there are numerous other sensors around. We have smart meters to capture energy consumption in smart homes, and various other sensors. In manufacturing, a couple of sensors that really monitor how our production processes flow. And these sensors create a vast amount of data at very high frequency, possibly. And if data is created at very high frequency, it also means that data gets outdated very quickly, which creates challenge if you want to, stay abreast of time and analyze relevant, i.e. current data. Numerous challenges arising here with respect to velocity. And big data is all that. So it's not only size, that's the key take home here. It's not only about size, it's also about at least the other 2 dimensions, velocity and variety, which were always part of the definition. And then, in my opinion, it was other players wanting to jump in, extending the term. It was kind of a game to come up with new terms that start with the letter V, to have this we model of defining what big data is about. Veracity, I believe, is due to IBM arguing that, okay, we have all this large and variable and high frequency type of data, or high velocity type of data, but the trustworthiness, the degree to which this data is reliable, or actually even factual, is a lot different from what it used to be. If you think of the data in a company that comes in through the ERP systems, there will be some issues that need data cleaning later on, but the data should be quite accurate. Much different from what we see in social media, fake news, for instance. So the veracity of data is different in the big data age, and that, yeah, it's true. Whether we need that as a definition, I don't know, but certainly IBM needed itself to be part of the big data game. So maybe this is where there we. And who do you think coined the value we in this then 5V module? Any suggestions? In fact, I'm not 100% sure that the data I have here is 100% reliable. So noting possible issues with veracity. As far as I know, that was done by McKinsey. So the, let's say, consultancy branch of the IT market. And indeed, data is not valuable in its own right. It must create value, for example, through supporting decisions or enabling better decisions. So that is big data. It's all about the data that exists. It is about the characteristics of data in our world, in our digital world, and where it comes from, like senders, social media, etc. To some extent, it's also, or used to be, hype created by IT players. This is why the lower right graph is there, to just sketch some buzzwords and technologies that exist in the open, in the big data realms. And depending on your understanding, whether you, for example, judge the value we, a core part of big data, then the overlap with analytics can be very sizable. Or if you say, well, it's more about the data itself, no matter what use cases exist, then the overlap with analytics is less developed. So this is big data versus business analytics. What is this all about? And lastly, the lecture is called Business Analytics and Data Science. To be honest, mainly because I was undecided which term I like better. One of them would have done the job. I don't want to go into details. If you ever came across data mining, if you manage to tell data mining apart from data science, please enlighten me, because I find it extremely difficult. My personal opinion here would be the red part, right? I would consider data science as the technology stack if applied in economic business type of context, translates into business analytics, but the technology can be used elsewhere, can be used in medicine, in biology, physics, wherever. It can be applied to process data, and certainly data exists everywhere. So data science is more general and thereby less geared towards certain applications than business analytics. Other than that, there is much overlap. For instance, the stack, descriptive, prescriptive, predictive. You have these three bits everywhere in data science as well. Okay, I hope that by now you have a good understanding of what business analytics is about, and some understanding how this term can be delineated from other terms that are popular these days. That was my goal. Any questions or comments on the definition part, which we can luckily now leave behind? Okay. You know, by experience, it's normally not the most exciting part of the lecture, I must admit. If we say that for this course and analytics more generally, when we speak about algorithms, we have two big branches: the predictive branch, techniques to turn data into forecasts, and descriptive techniques to summarize data and help us understand complex data. Then this tree shows you sub-categories in each of these branches. Regression is a term that all of you know well. Classification maybe. Segmentation probably as well. And rule sequence mining. This is the kind of summary picture of the techniques that are popular. It's not fully comprehensive. There are more, for sure. But it's a good first, landmark or map. Provides us some guidance. And I want to look with you today into the segmentation part, which we see is one flavor of descriptive analytics. And then in order to carry out segmentations, whatever that is, we'll see in a minute, you have various algorithms. So the lowest bit in this tree would be concrete algorithms that we can use to do segmentation, k-means for instance, or to do regression, where we could use linear regression, or equally a neural network, or something else. And this is how to read this tree. Modeling branches, different models maybe, regression models, segmentation models, and different algorithms to build corresponding models. That is maybe important. We speak a lot about model. A model is something that you obtain by applying an algorithm to data. That's how these terms relate. They're not always, very well delineated, but probably they should. So this would be my take on this distinction. What's a model, what's an algorithm, and how they relate. Now, cluster analysis. Here we try to have a model, an empirical model, so based on data, the point of which is to summarize data and give us a high-level overview of the data, taking out the details and thereby enabling us to better understand what the data is about. A cluster is a subgroup. All data, i.e. all data points that are available, all customers that have been observed accessing our website last week. And within that data, we look for subgroups, stereotypes maybe. We shouldn't stereotype humans, but we should stereotype data. And cluster analysis is a vehicle we can use to do so. First of all, before going into more details here, the graph is very important to me. Or more specifically, what is really important to me is that you are 150% sure, and maybe I shouldn't use the term 150% in a quantitative lecture, how this graph translates into a table, and how tabular data, the data I said will accompany us for the next 15 weeks to come, is equivalent to this graph. Because I can plot in 3 dimensions, not to mention more than 3 dimensions, I just have 2 dimensions here. The number of purchases and the average order volume. These are 2 characteristics that we could use to describe customers, clients, let's say. How often do they buy? And how much do they spend on average? So think of these as 2 columns in a data table. And then a data table would have other columns, but then I can't draw it anymore. But in tabular data, you should look at tabular data, or you should understand tabular data as a summary of data points. These are the rows, and each point lives in a multidimensional space. 2 columns, 2 dimensions. Then I can draw more columns, more dimensions. I can't draw it anymore, but the still concepts apply. Mathematically, it's easy for us to work in n dimensions. Visually, that's not so possible. Maybe some of us also have some, difficulties in thinking in n dimensions. I would count myself in here. But algorithmic operations, mathematical operations, nicely generalized to n dimensions. My examples will always stick to 2 dimensions. So I'm envisioning a table with only 2 columns. And then a single point in this 2-dimensional space is a row in this table. It's a data point, an observation. So this guy here, right? That is a customer. Maybe it's John. And for John, we know that his average order value is whatever that is, maybe $120. And also we know about John how often he typically comes to our shop to buy something, maybe every month. And this is how we interpret all the other data points. And then certainly you look at that graph and you immediately see, come on, story is clear. We have 3 clusters here. That's so obvious, and it is. It really is. We have 3 groups of customers, these 3 groups. Could you help me by, so this is the result of us as data scientists doing some fancy data analytics, presenting that to management. What is the story here? Who can tell a data narrative? Note that word, data narrative. We need to be able, as data scientists, we need to be able to tell data narratives. Please, what's your narrative? Precisely. That is a very nice description of what we see in the graph. And you referred in your answer to the size of these groups and how they differ. Do you have any suggestion to label these groups? The description was 100% accurate, but what could be a label? So this large group of customers, you say they purchase very often, typically for smaller amounts. Any suggestions how we could label them, stereotype them? Or any other group for that matter. Maybe other groups are easier to label, to stereotype. So these are then the good guys. It's maybe a bit informal. If we are in a hip, young startup, that's maybe our terminology. If we are a bit more conservative type of companies, maybe we call them premium customers. But it's, as a matter of fact, it's the same, right? Just words. So indeed, they buy often, they spend a lot. How good can it get? Any suggestions for the others? If we label or try label groups by referring to the attributes, that is going to work in 2 dimensions. If we call these the high purchase, low order customers, that works because we have only 2 dimensions. If we have 6 dimensions, it's not going to work anymore. Because then this would be the high purchase, low order, young from Berlin, weekly buy. You see how this breaks down. And normally in real world data, we have not only 2 dimensions, we have dozens, maybe hundreds, maybe thousands. So we need higher level concepts to label them. Wonderful. You see, this is exactly what it means to tell a data narrative. You look at the attribute values and you look at what characterizes this group, as you did, right? As all of you did. And then you're trying to find out, okay, what does that actually mean? What is it? So they come very often, but buy very little. And then depending, well, you know, to really conclude this, we would need some more context. What type of product is that they buy or don't buy? And you come up with the proposition that would probably fit very nicely in some context. Hey, maybe these are the spontaneous customers. Possibly, absolutely possible. And it's a way to summarize the pattern that we see in the data. Maybe these are the budget-oriented people. Yeah, possibly. And again, with some more context, we can come up with other labels. And please note, no matter what fancy a clustering algorithm we use, this task, which is arguably the most important task in descriptive analytics using cluster analysis, you will get no algorithmic support whatsoever. So this is where the business expertise, the domain knowledge kicks in, hopefully, to really find out what it means. The algorithm takes care of finding these groups. Budget-oriented, spontaneous, transactional. You could also call these customers transactional. That's maybe management jargon. And for the blue groups, it's even harder. Maybe you here would come up with a term like else or other or undecided. These are harder to characterize. But this is really let's say this is a workflow. You have data. You use a cluster, bring algorithm to group the data and find the subgroups. And then you coined the term centroid, which is referring to the midpoint of a cluster, where we might calculate something like an average over the attribute values of these 3 points. So the average order value of the 3 customers in that cluster. This is how we could identify a centroid, a hypothetical customer that has not been observed, but who is representative for this subgroup. And then based off the centroids, we could try to create our data narrative, look at the values of the attributes, and try to reason what it means. Maybe it's the budget-oriented type of customer. Maybe it's something else. So actually, the algorithmic part is trivial, right? The algorithmic part means that you identify the 3 clusters. don't think that anybody of us would have a hard time to do that in this example. It's not hard to see there are 3 clusters in the data. Why do we need algorithms to do that? Why can people get a PhD for coming up with a new clustering algorithm? Which is something extremely noble and prestigious, by the way. It's a toy example. If we have 20 dimensions, seeing clusters is not at all possible anymore. So the key feature and the key deliverable of our algorithm is it can work in n dimensions while we can't. Okay, now many business applications around. Here is a little list. Don't want to go through too much detail. Marketing is a common use case. Cluster customers. It's also a common technique in natural language processing, where we might want to cluster, I should say, to segment, to group documents. Maybe to create something like an index. And it's used in fraud detection as well. A cluster is a group of observations that are similar and that can be distinguished from other observations. And any observation that is not similar to any cluster that we know, that is abnormal, could be considered suspicious in a fraud detection setting. So cluster analysis is a very important topic as well in the scope of fraud analysis, which has something to do with detecting outliers as well. So many business use cases. Let me walk you through one example, a marketing example, which refers to a project, real-world project. So we did this project with a major player in the DIY market, do-it-yourself market, companies like the ones I illustrate here. And the business problem was to target these leaflets, these little, leaflet catalogs that you get together with your daily paper or as unsolicited mail in your post box. And when doing this project, I was stunned to learn how much money they spend on that, which was a figure in the hundreds of millions of euros, and it was not the lower end of the hundreds of millions of euros, for a company with 7.5 billion annual turnover. I would not have expected that to be such important marketing channel. Apparently it is. Especially in Berlin, I get basically drowned in these leaflets. Maybe you have a similar problem, or maybe you are not as, I am too lazy to put this no advertisement on your postbox. So it's used heavily. That is my personal experience. And the question is now, from the company perspective, how do we target that? How do we know where to ship these leaflets? That was a business problem, was a major advertising channel, and we approached that using cluster analysis to improve the targeting of these marketing materials and eventually, hopefully, raise return on advertising. It was very clear early on that individual level targeting marketing communication, i.e. leaflets on the level of an individual customer, is infeasible. Why? Individual level targeting, very hard to process. Remember, it's a do-it-yourself company. You probably have found yourself in a Bauhaus or Obi store when you moved in your flat, right? They don't know so much about the individual customers. Maybe if they have a loyalty card, they can identify individuals. The majority of customers, they can't. Who has a loyalty card from Obi, Bauhaus, or any other? You see my point. Well, maybe we're just not their target profile. Okay, so individual level targeting infeasible. The decision-making unit here was the aerial unit, i.e. the zip code. They did targeting at a zip code level. So you ship a leaflet in a certain zip code or you don't. That's the business question. Hence, the way that the form of support that was thought here is basically a list of zip codes per individual leaflet. There is not one leaflet. They have maybe the weekly one, Then they have seasonal leaflets, the summer, the spring, the winter catalog, let's say. They have specific forms for special offers. There are different types, and for each type of these leaflet, of these, well, let's call it a catalog for simplicity, we need a targeting, which zip codes should be solicited. And to answer that question, we will look into the profile. What is the profile of a zip code? Now, if you need to make decisions based on a zip code level, how would you picture a zip code? What is a zip code? How does our multidimensional attribute space look like? If we talk about zip codes, what information do we have about zip codes? Yes, rural, urban. That we know. That could be a variable with two levels. Number of people living in that zip code, average age. How do you know that? Refer to some official sources, private sources like Google or Facebook, yeah. Okay, I would not think of these players as my first list. Maybe they also market that data. Open data possibly. Very good, very good. Okay, so trying to summarize. There are players who have data that characterizes zip codes, and maybe they sell this data to us. In fact, there are indeed companies in Germany. There is GfK and there is Nielsen, for instance. Very big players where you can buy data that characterizes aerial units, zip codes. You can buy this data not only for 5-digit zip codes, but even for 7-digit zip codes. Maybe you didn't know these exist. I didn't know they exist when entering this project. There I learned. So it's quite fine-grained. Another point that you raised is, hey, I know where my store is. It's an offline business. It's a bricks and mortar business. I know where my store is. Maybe there is a way to find out by the people who come to that store a possible hypothesis or a plausible hypothesis is that if you go to an Obi store in Berlin central area, I'm not sure there is one, anyway, then it's quite possible that you live in the area, because why would you go to that store? And you probably have experienced that yourself, that when you buy something in the store, you are asked for your zip code. So would you mind telling me your zip code? This is how they pull this data, because then I have your bill, I know what you bought, and I know where you're from. And with this information, I can also enhance my understanding of your zip code, taking you as an example. That's another way to gather the data. So yes, we had data available from these market research agencies, like the number of households, their household income, the number of kids, whether there are kids, academic degrees, number of pets. It's really interesting to look into these sources and what they know about the area where you live. I invite you to check out the offering of these companies. Like go to GfK or go to Nielsen. Many will allow you to key in your zip code and then show you what they know about this zip code. It's interesting, fascinating, scary. A mixture of these emotions which basically come. Anyways, so if this is what characterizes a zip code, and we make decisions based on this zip code level, we can profile zip codes. This means nothing else but we analyze the plot, which has the individual attributes, the dimensions, and then we just look at the value for this dimension, how many households there are in a zip code. This type of graph, a polar plot, generalized to a decent number of dimensions, not thousands certainly, then the line would be too long. But if we do not have too many dimensions, then we can make sense out of these plots, look for similar zip codes for different zip codes. And then let's say, based on our past experience, we know, let's not go how, but let's say we know that a certain type of leaflet, has worked well in a couple of zip codes. There are ways to check whether people buy based on a leaflet, whether the leaflet drags people to the store to buy something that was advertised there. There are ways to find that out, for example, using coupons, if you think about it. This is why people use coupons, or it's one of the use cases for coupons. So this is what our client knew. The blue line depicts the average profile, the profile of an average zip code, where a certain type of leaf node was known to work okay. Now, seeing the green and the red zip code, which one would you select if you have bought it to target your leaflet or to ship your leaflet in one of the two zip codes, the red and the green? Which one would you pick based on your knowledge of where this leaflet usually works okay? The red one. Sorry, the red one? Okay. Who else? Why do you like the red one, by the way? Fair enough, but this is very much based on, we could call it domain expertise, or we could call it gut feeling. There is similarity between these terms. Okay, you noticed that I was surprised by this answer, so it's clear what would have been my suggestion. You have a prior opinion which dimensions matter and which matter less. I take from your suggestion and from your explanation. Let's say we do not have that. We believe all dimensions, all attributes are relevant. Otherwise, we would filter out those that we think do not matter earlier. If they are all relevant, and then the question would be, how do we calculate the distance between lines? There are answers to that, but there is no single way to do it. But if we just eyeball this graph and compare the lines, then yes, the behavior of the green one and the blue one look more similar than the blue one on the red one. With respect to the attribute bachelor degrees per household, it's specifically clear where both green and blue have a slight upward trend. Also, with respect to the number of households, we do observe a notable difference, and with respect to income and the number of no-kid households, green and blue follow a similar tendency. So, judging all attributes as equally important, we would establish that the green zip code is more similar to the blue one, and if we believe the blue one is sort of representative of where the leaflet works, it would be plausible to ship the leaflet to the green zip code. So what's the take home here? Cluster analysis is often used to develop profiles. And profiling is another term that sounds very cool. There was a TV series, The Profiler. Maybe you liked it, maybe you don't even know it. It's an old one, so probably it's me knowing that, and you don't. Anyway, profiling it sounds very interesting, I believe, but what is it all about? What we just looked at is an example of profile. We have profiled our zip code. We created a profile of a zip code. Or going back to the earlier example of customers, these polar plots here, you can understand them as a profile, a way to depict the profile of an entity, a zip code, hypothetical customer, or more generally a cluster. Cluster analysis is about finding subgroups in the data, and these subgroups could take the role of helping to profile a certain group of customers in marketing, credit card transaction in fraud screening, or web pages in text analysis. And then these profiles would allow us to abstract from the detailed level all the individual data points, all the customers, all the credit card transactions, all the web pages, which are so massive that we can't cognitively process them. And by looking at the profile, the cluster centroid you said, right? We can summarize the data and then understand the data and make decisions based on the data. For example, by comparing profiles to one another, looking for similarity. That is a way how you can support decisions using cluster analysis. It's not the only way, it's one way. Okay, so now the next thing would be to see how this works, at least briefly. Just my PowerPoint thinks we should stop here, and I believe it's a bit too early. Cluster analysis methods. Now we leave the use case and come to the algorithms. I will basically rush this part a little bit because I believe that many of you have seen that. You can categorize algorithms into different branches. Some work in a hierarchical fashion, others work in a non-hierarchical fashions. Those you can further split, maybe in hierarchical algorithms that either follow an agglomerative paradigm or a divisive paradigm. But no matter what type of cluster technique you consider, no matter whether it's old and established or super new, every technique is based on the notion of difference or similarity, difference or similarity. And this is also what we applied early on with our profiles, comparing the blue line to the green line. It was a similarity comparison by eyeballing. Algorithms can't eyeball. We can eyeball. We need to be a bit more formal, but it always cooks down to a comparison or measurement of similarity. And this also helps us to be a bit more formal in describing what cluster analysis is about. Finding subgroups in the data, yes. What is a subgroup? And using the concept of similarity, you could say, well, you know, a subgroup is actually a set of observations that are similar to one another and dissimilar from others that do not belong to the same cluster. And there are two sides of the same coin. You can basically say the aim of clustering is then to maximize the similarity of the observations in the same cluster, intra-cluster homogeneity. Or you could say the aim is to maximize the dissimilarity between observations in different clusters, so maximize inter-cluster heterogeneity. But both come down to the same type of problem or task. And you need a way to measure similarity or the lack thereof. So you need the distance measure. And again, there are many choices available. There are many formal ways, mathematical, rigorous ways to measure distance. Any distance measure is a function of two inputs, the two objects, the distance of which you want to measure. And any distance measure is a function that produces exactly one output, a numeric value that, when large, says the two inputs are dissimilar, and when small, saying they are similar. And this is actually a very general concept. So looking at the plot, a final time, of course, we have data points and we have attributes like the number of purchases and the average order volumes numbers. So we could easily draw on our background in math and start and calculate the difference between, or geometry for that matter, the difference between the points. But distance is more general. You could compare the difference between images. Text, it's just a function of two inputs that produces one output. Is the two inputs, are they similar or not? That's the distance. For numeric data, the family of LP metrics is a very popular example, and the Euclidean distance maybe is the most popular example to measure, right? We really want the single number output to measure, given two objects, their distance, their Euclidean distance. You see the formula, you have seen them before, so we don't need to go into the details here. And the Euclidean distance, although being probably the most popular and prominent example, is only one example in a wider family of distance measures or metrics called the LP metrics, the formula of which you see here. And depending on how you choose P, your distance functions will display certain properties. I think the three, if we look for the top three common choices here, it would be to set P equal to 1, then you obtain the Manhattan or city block metric, which you see depicted, or you set P equal to 2 to obtain the Euclidean distance, or you set P equal to infinity to obtain the infinity norm. It's most known under that label or term. What are the properties of these examples if you compare P equal to 1 to P equal to 2? This is, by the way, an important comparison. What are the properties of the resulting distance measure? Or maybe if you compare P equal to 2 Euclidean standard to P equal to infinity, as high as it can get. You see these measures and you see how they process n dimensions. These distance measures work in n dimensions. I'm showing that again for 2, but the formula you see k equal to, or from how they run over multiple dimensions. So they generalize to n dimensions. When we set P equal to infinity, the difference between two objects will be exclusively determined by the single dimension out of all m dimensions where the difference between the two items is largest. And this single dimension where there is the largest difference between the two items or their attribute values, because the exponent is infinity, it will be amplified a lot and it will overshadow all the differences in other dimensions. So the higher P, the more will our distance measure focus on some dimensions where there are large differences between the two objects' attribute values. That's one of the things to note here. Other measures, popular measure is the cosine distance that is also used a lot, especially in text analysis, where you say, you know, a data point I can understand as a vector in a multidimensional space, and a vector I can understand as a straight line from the origin all to this point. The blue bolts are again two data points, and then I have two vectors, and the angle between them actually is my measure of distance. You can also, I mean, not sure, but you have done something in statistics. If you look at mean square error as a forecasting measure, mean square error compared to mean absolute error, it's the same story. Do I want to look at all differences, or is it really the large differences that are my key interest? And if the large difference is my key interest, by putting a high exponent, I will basically emphasize this large difference. That's it. Now, so many different ways to measure distance. Euclidean being most common. Second, probably cosine, or maybe the L1 norm, the Manhattan distance. The thing is that they differ, and this is what I'm trying to show here. Looking again at the two data points, the blue line is the Euclidean distance, and you know, just roughly by eyeballing again, the Euclidean distance says, okay, these two data points are different. There's a large difference. The line is long. There's a large difference. That's the story of the Euclidean distance. Whereas the cosine distance says, no, they're not. They're quite similar. Both of these measures are absolutely established. There are certain properties that a true metric must fulfill. Both of them are okay. Both of them are used. They're okay. They exist. And still, in this toy example, they tell an entirely different story. We can't help that. That's the issue with clustering, or a problem. You need to pick a distance measure, feed that to your clustering algorithm, and this measure that you feed to the algorithm will have an enormous impact on the algorithm's result and how the algorithm carries out its task. And if anybody is able to identify a suitable distance measure in a certain application, I congratulate you, because this is typically very hard to say the least. So what happens in industry, typically we just pick the Euclidean distance and don't worry about it, hoping for the best. But what I'm trying to say here is, with cluster analysis, there are some problems in judging the quality of solutions, one being that the distance measure has an enormous impact, and there's virtually no theory that would help us to tell which measure is a good choice in many cases. That's just a cautionary remark. One more positive remark is, note how distance is a very general concept. Here I exemplify a possibility to measure the distance between two pieces of text. And the example shows you the string added distance, where we basically count the number of operations that we need to turn one string, Peter, into another string, Piotr. Here it's easy because the strings have the same length, but we could generalize our distance measure for strings of arbitrary length. And in general, the number of added operations that we need to transform one string into the other is a way to capture how different they are. And intuitively, we would be able to say that Peter and Piotr, these names are more similar than Peter and Mary. It's intuitive, even if we don't think about how we actually measure that. That's an example. And coming up with a nice way, there is no perfect, there is no optimal way, a nice way to capture difference. I mean, this is how applications like Spotify can be created. Powerful, wonderful applications that we love using. How do I come up with a good recommendation what music you might like? I look at the stuff that you hear and maybe like, and then I try to find something similar. And audio there's just an audio wave, so why not clustering different songs in the frequency spectrum? Spotify does not work that way, I think, but you could create a recommender system in that way. And for audio, there are some use cases online with which you can play. I think I've seen some examples. With audio, it works quite well. It wouldn't really work well with video. You can think of why it wouldn't work well with video, but this notion of distance is really general. Okay, let's look at one example for a concrete algorithm. Let's look at the workhorse. If there is one algorithm that you want to single out as the most popular, well-known, whatever, would probably be k-means. So let's look at k-means. So this is where k-means fit in. It's a non-hierarchical technique that performs exclusive clustering. We have the pseudocode here. Define number of clusters k. So this is a user input. Randomly guess cluster centers, i.e. the centroids. Assign cases to nearest centroid to obtain an initial solution. Update centroids, assuming correctness of the current solution. Repeat until cluster assignment stops changing. Okay, nice. Once we understood the algorithm, this pseudocode will make a lot of sense. And here's also a formal way to depict the objective, which is a minimization problem. So this is a way to formalize what minimize the intra-cluster variance means. We look at the data points in one cluster, calculate their pairwise, their variance, not pairwise, take that back, calculate their variance. The larger this variance, the more dissimilar the objects in this cluster. So this is what we want to minimize. And we want to achieve that over all k clusters. To not have one cluster perfectly pure and the others displaying much variance. This is not what we want. We want to minimize this intra-cluster variance across all the clusters. So this is the first sum in my equation. But actually, I like graphs better than equations. So let's look at a toy example once more. Yes, please. Is there an algorithm to define the number of clusters? No, there isn't. Any non-hierarchical technique needs the user to decide on that, and since there is no theory. Sometimes the application will dictate a choice, or at least narrow down the choice of K, getting there shortly. And if not, one typically performs an empirical analysis to find out what might be a good solution. Be with me for a second, we're going to get there soon. And we have to, because it's less than 50 minutes left. Two-dimensional example. I did not bother putting labels on the axis. That's very bad style. If you do a graph, always put labels and know when you are allowed to deviate from the rule. Now you must be able to appreciate these pictures, right? We're simplifying things, imagine only two attributes, and then the data points are the rows of a data table, etc., etc. Oh, we want to cluster that data, say. Now, let's assume we fix K to 3. Why? Because 3 is a nice number. 3 is good. If you have votes, then you will end up with an unanonymous decision. 3 is a good number. So let's say we want to have 3 clusters, and let's randomly guess 3 centroids. Red, green, and blue. What does it mean to say we randomly guess a centroid? Well, if we have 2 dimensions, every data point is characterized by the values of these 2 attributes. So randomly guessing a centroid translates into randomly guessing 2 numbers, one for dimension 1, let's call it x1, the other for dimension 2, let's call it x2, and then by the 2 numbers that you randomly guess, you can basically put the point in this space, and this is how I created these 3 hypothetical centroids. Now comes the next step in K-means. I need to determine the clustering solution that these 3 centroids dictate. Let's find the connection between these 2 vectors. Let's find the separation between these 2 centroids as the orthogonal vector. So these 2 centroids allow me to cut my attribute space in 2 halves. And I can do the same with the other centroid and the last one as well. And then in the end, I obtain this separation, which basically, what was with the orthogonal vectors all about. Essentially, this is the way to mathematically determine which data point is closest to which centroid. This is your goal. And this little animation was just to sketch how this works mathematically. But essentially, the point here is that you have 3 centroids. You find out which data point is closest to centroid number 1 and 2 and 3. And then you say, okay, every data point belongs to the cluster of the centroid that is nearest to it. So this way I obtain my initial clustering solution and can now establish for all the data points whether the point is in the red or the blue or the green cluster. But once I have that, I can basically make the next step saying, oh well, you know, if now I know which data points are red and green and blue, which belongs together, I can find the centroid for these data points. Or mathematically speaking, I could calculate the average of the attribute values of the data points that belong to the same cluster. And this will result in my centroids getting updated. They will move closer to where the mass of the data is about. So the red cluster centroid will move more to the center of all the red data points, which I'm trying to sketch with the arrow. I count on the ability to improve this poor initial solution in the process of the algorithm, and here you see how I improve it. I let the centroid now move closer to the center of the data points in the same cluster to be, let's say, more representative of the red and blue and green data points. I calculated the distance for each point to every centroid and found the closest one. Now, once I have updated my centroids, I will come up with a new clustering solution. The centroid is a set of random values, and in a two-dimensional space you need two random values, one for x1, one for x2, and in an n-dimensional space you just guess n random numbers and make this your centroid. You're asking that if you start from a random initial solution, would that solution not impact the final result a lot? And the answer is yes. And then you say, should you then rerun this multiple times with different random start points just to repeat what you were saying? And this is also correct. This is what you would do in practice to be a bit more robust with regard to the initial random solution. But no matter from which random solution you have started, it will be possible to identify the closest random centroid for every data point. And this operation, which I am highlighting here using the three orange lines, gives you your initial solutions. And with this initial solution, I color the data points, so I now established which data points belongs to which cluster. And with this information, I can update my centroids by now simply calculating, for example, the average of all the red and green and blue data points. And this average will basically give me the updated centroid. So these arrows mean I'm trying to find the center of the clusters, and this is maybe where the graph is not accurate. I'm just trying to draw the arrows in such a way that they point to where the central point might be. And then my centroids would move. But if the centroids move, my partitioning of the data points also changes. So this point will now get updated. So it's green in the previous step of the algorithm, but now I have updated my centroids, and I repeat the step where I find for each data point the closest centroid and assign the data point to the corresponding cluster. And now you've seen that the solution has changed a little bit, and the upper left data point is now assigned to the blue cluster. And because there just was an update of the clustering solution, some points have changed their cluster assignment, I can update my centroids again. And by now you will hopefully see that it is a back and forth between two steps. Updating the centroids and updating the cluster solution based on the current value of the centroids. And you do this back and forth. It's an iterative algorithm. You do this back and forth until some stopping criteria is met. For instance, you could just check, did any data point actually change its cluster assignment? If yes, continue. If no, stop. Or you could say, as a rule of thumb, do this 20 times and then it's enough. There are various ways to terminate the algorithm. This is how k-means work. And indeed, because you start from an initial random solution, you want to do this multiple times. And at this point, it's actually important. You want to average over the results of this, let's say, 20 runs of k-means. 20 is a common setting. What is the actual output of k-means? What do you get? The algorithm was such that we need to give k. K-means doesn't give us k. So it does not even, if you want to be a bit critical, it does not even give us the number of clusters. We must give it to that. All it gives us is the assignment of the data points to the n clusters, whereby we set n or k for that matter. That's the outcome of the algorithm. And this is something that we as analysts must then post-process in any way that we deem suitable. You can also calculate the final centroids and then use these as profiles, as was shown to you in the use case, the leaflet targeting use case. That is something you can do. Or maybe you just were interested in knowing which data points belong together in a cluster. That's something what you get, but you do not get anything else. For any richer way of decision support, you need additional techniques or just your expertise. And okay, the time is up, but to conclude the k-means part, k, there is no theory I said to determine k. Please look through the slides where I exemplify how k is typically determined empirically by trying out different settings of k and then checking the value of your objective. Give me 1 minute, please. And in this stylized example, I depict the objective value, which was the sum of the intra-cluster variance. Remember, this is what we want to minimize, as a function of k. And then we try to spot an elbow in this graph where we say, making k any larger than that does not really give us a large gain in our objective. So here we would stop maybe with 2 clusters. And that was very brief, I know, but do not worry. You will do this on your own in the tutorial, and then everything will further clarify. Thanks a lot, and I'll see you next week.